A PN junction with two metallic contacts is known as PN junction diode or semiconductor diode. Semiconductor diode is formed when the trivalent impurities are introduced on the one side and pentavalent impurities are introduced on the other side of a single silicon or germanium wafer. For example, if this is the silicon wafer and we introduce trivalent impurities on this side, then we will have p-type material, and if we introduce pentavalent impurities on this side, then we will have n-type material. And these are the metallic contacts, and we have a semiconductor diode in this way. We can apply the external voltage across these two terminals, and depending upon this we will have three cases: no bias condition, in which we do not apply any external voltage; forward bias condition. In forward bias condition, P side is connected to the positive terminal of the battery and N side is connected to the negative terminal. And the last case is reverse bias condition, in which negative terminal of the battery is connected to the P side and positive terminal is connected to the N side. We have already completed all these three conditions, and now we will see how diode is represented in circuit. That is the symbol of PN junction diode. This is the symbol of PN junction diode. We apply external voltage across these two terminals, and this side is P, and this side here is N, and this vertical line is depletion layer. This is the representation for depletion layer. So we have three things in the symbol of semiconductor diode. The first thing is the P side, this one. This triangle represents the P side. Then we have the depletion layer. This vertical line represents the depletion layer, and after depletion layer we have N side. Let's try to forward bias semiconductor diode, and this time we will use this symbol. So forward bias condition, forward bias condition of PN junction diode. I will make this symbol. This represents the PN junction diode. And in case of forward bias condition, the P side of the diode is connected to the positive terminal and the N side of the diode is connected to the negative terminal. So we will connect the P side to the positive terminal and we will connect the N side to the negative terminal. So this is how forward bias circuit looks when we use this symbol. And let's say applied forward potential is Vd, and the current through the diode is Id. This is the current through the diode, and Id is equal to I majority, current due to majority charge carriers, minus Is, where Is is the reverse saturation current. Now we will do the same thing for reverse bias condition of PN junction diode. First we will make the symbol of PN junction diode, and in case of reverse bias condition, the P side of the diode is connected to the negative terminal and the N side of the diode is connected to the positive terminal. So we will connect the P side to the negative terminal and N side to the positive terminal of the battery. This is Vd, the reverse bias potential, and in case of reverse bias condition, the only current is reverse saturation current, that is Is. So this is the only current in case of reverse bias condition. So this is all for the symbol of semiconductor diode. Now we will move to diode current and diode voltage relation. Diode current and diode voltage relation. And diode voltage relation, and this is very important expression. And the diode current and voltage relation is given as ID is the diode current, is equal to Is, in bracket we have e raised to power small k Vd by Tk minus 1. So this is the diode current and diode voltage relation, and we will use this relation in solving numerical problems, and you will have one question in your exam depending upon this formula. In this ID is equal to diode current IS is equal to reverse saturation current, and VD is equal to voltage across the diode. T subscript K is temperature in Kelvin, and if you have temperature in degrees Celsius, then add 273 degrees Celsius to the temperature in degrees Celsius. Small k is the Boltzmann constant, and it is given as 11600 divided by eta. Now eta is very important, and eta is ideality factor, and ideality factor is the function of operating conditions and physical construction, and it has range between 1 and 2, and this range depends on various factors. Now we will see the ideality factor for germanium. It is equal to 1 for germanium, and it is equal to 2 for silicon, and this is when the ID, the diode current, is low, and when diode current is high, eta is equal to 1 for both germanium and silicon. This is when diode current is high. So we will use these values in numerical problem, and we can modify this formula because we already know VT, the thermal voltage, is equal to Tk, temperature in Kelvin, divided by 11600, and from here we can see K is equal to 11600 by eta. So we can say 11600 is equal to K multiplied by eta. So we will replace this by K eta. Now from this equation we want to replace K by Tk. So let's do this. K divided by Tk is equal to 1 by Vt eta. Very simple. K divided by Tk is 1 by Vt eta, and now we will replace this, and we will have diode current ID equals to saturation current in bracket e raised to power Vd divided by eta Vt minus 1. So from now onwards we will use this formula for the diode current because it is very easy to implement. Let's solve one problem based on this formula. In this problem we have to find the reverse saturation current. A germanium diode displays a forward voltage of 0.25 volts at 10 milliampere current at room temperature. Find the reverse saturation current. So we have Vd, the voltage across the diode, and it is equal to 0.25 volts. It is equal to 0.25 volts, and we have diode current Id, and it is equal to 10 milliampere. Diode current Id, and it is equal to 10 milliampere, and all these values are given at room temperature. So temperature is equal to 27 degrees Celsius. Now we will convert it to Kelvin. So temperature in Kelvin is equal to 273 plus 27, and it is equal to 300 Kelvin. So this is the value of Tk. Now we will calculate Vt, because it will be used to calculate the reverse saturation current, and Vt is equal to Tk divided by 11600. Tk is 300, so we have 300 divided by 11600, and this will give us 0.026 volts. Now we have everything to calculate the reverse saturation current, Is. We can easily calculate the reverse saturation current, and the formula is Id equals to Is in bracket. In bracket we have e raised to power Vd divided by eta Vt minus 1. This is the formula, and eta is equal to 1. Eta is equal to 1 because we have germanium diode, and for that eta is equal to 1. We have Vd, it is 0.25. We have Vt, it is 0.026. Eta is 1. Id is 10 milliampere, so we can easily calculate reverse saturation current, Is. 10 is the value of diode current. Is e raised to power Vd is 0.25 divided by 1 multiplied by 0.026 minus 1. In the next step we will divide 0.25 by 0.026. I will use scientific calculator for this purpose. 0.25 divided by 0.026, and it is equal to 9.615. It is equal to 9.615 minus 1. In the next step we will calculate e raised to power 9.615. I will use the calculator. E raised to power 9.615, and this will give us 14987.922. 14987.922 minus 1. So we have 14986.922, and Is, reverse saturation current, is equal to 10 divided by 14986.922. In the next step we will divide 10 by 14986.922. So 10 divided by 14986.922, and this will give us 6.67 multiplied by 10 raised to power minus 4 milliampere. So this is the value of reverse saturation current, or we can write it as 6.67 into 10 raised to power minus 7 ampere, or we can write it as 0.667 into 10 raised to power minus 6 ampere. 10 raised to power minus 6 ampere is 0.667 microampere. So the value of reverse saturation current is 0.667 microampere. It is very small current, and I have already told you reverse saturation current is a small current. So this is all for this lecture. See you in the next one.